So now let's start building our first topic regarding discrete variables, which is a sequence. A sequence is an ordered list of numbers of the form a sub 1, a sub 2, a sub 3, and so on. A sequence may be generated by either a recurrence relation of the form a sub n plus 1 equals f of a sub n. Now, did you notice that? N plus 1 is the next value in that sequence after a sub n. So it's saying, hey, the next one is defined by the last one, or the most previous one. And then A1 must be given in those cases. And then a sequence may also be defined with the explicit formula A sub n equals some function of n. Now we'll use both of these, so we kind of want to look at them a little bit more. But I also want to mention really quickly that this recurrence relation has two components. A sub 1 has to be given, and a sub n plus 1 has to be a function of a sub n. This is also called an implicit formula. You're defining your sequence implicitly by the most previous portion. Sorry, my eye looks really strange there. Implicit. There we go. All right, as opposed to an explicit formula down here, which will define it as some function of n for n is equal to 1, 2, and 3, which is the natural numbers right here with an extra bar in it, like that. Or sometimes we'll define it as 0, 1, 2, 3, and so on. So sometimes we'll include 0, which is the whole numbers, and sometimes we won't, and we'll just start at 1. We'll do it both ways, so be prepared for that. It's not really a big difference, but there are just times where it's more advantageous to use the whole numbers versus the natural numbers and vice versa. Sorry, I'm unhappy with my capital N there. There, that's better. And this is what I was just saying. It's like on the planet. Sometimes we start at 0 instead. That's all this is saying. So sometimes it's convenient to start at 0. Then we'll start at 0. That's all. That's a lot highlighted, but it's really, there's three different things going on. You've got your recurrence relation, which is in orange. You've got your explicit formula, which I've got in green. And then there's this whole, hey, sometimes we start at 0. Okay. So we're going to consider the following list of numbers. And again, it's up to us if we want to. I mean, at this point, we don't know, why we would want one versus the other. So we could think of this as the first term, second term, third term, fourth term, and so on. So this list is called a sequence. And each number in that list is called a term. So those are definitions. So I will highlight them, right? So the list itself is a sequence. Each number is called a term of that sequence. All right, so we can denote this sequence by two different ways. So we can write it out as three different ways. We can write it out as a list, a sub 1, a sub 2, which is kind of what we're doing right here. A sub n from n equals 1 to infinity, right? Because it keeps going ... so it's going to infinity. Or just a sub n. So those are the three ways that we define it that way. And if you see that a sub n in there, that a sub n is usually an explicit formula, right? But it doesn't have to be. All right, so this a sub n, this a sub n, this a sub n. If you're going to write it that way, then, well, I take it back. If you're going to write it that way, you should write it as an explicit formula. I'll show you how to write one for an implicit formula when we get down to it. And then one other definition, which is the subscript. So those little subscripts are called an index. They're associated with the ordinal number that goes with it. So that natural number, n equals 1, n equals 2. So they're associated with the ordinal numbers, right? Because you're thinking it's the first, it's the second, it's the third, it's the fourth. So if you will, this is a sub 1, this is a sub 2, this is a sub 3, this is a sub 4, and so on. So you're saying that's the fourth one, so it's a sub 4. That's the fifth one, so it's a sub 5. But of course, we can associate those with the natural numbers as well. And we are by writing that subscript 1, 2, 3, 4, 5, right? So what we're doing is saying, hey, this is 1. If I look at my n values, this is 1, this is 2, this is 3, this is 4, 5, right? First term, second term, third term, fourth term, fifth term, sixth term, dot, dot, dot. All right. Now we want to define this sequence in 2 ways. The first way we're going to define it is a recurrence relation. So I want to find the next number based on the last number. So I want to figure out how I can get from 1 to 4, but then from 4 to 7, and it needs to be a consistent thing. When you make a recurrence relation, you have to define a sub 1 or a sub 0. Oh, aka, right? So just, I'll sometimes call them recurrence and sometimes I'll call them implicit. They're the same thing. So I just want you to get that. Okay. All right. So if we're going to do a curly braces, we can't kind of work with these because they're explicit. So it needs 2 components. It needs that a sub 1 is equal to 1. Right? My first term was equal to 1. And then my next term, a sub n plus 1. All right, how does the next term relate to the last term? This can be some of the hardest things to do in these problems, which is you kind of have to think, hey, I'm adding 3 every time. So if I take my last term, whatever that was, and I add 3 to it, I'll have my next term. It's a recursive pattern, right? So I have my starter right here. So that's your starter value. And down here, I've defined my recursive pattern, or recurring pattern, if you will. That's how an explicit or an implicit formula, excuse me, works. All right, now what about an explicit formula? Well, let me remind you how this worked. So if we look at our sequence, a sub n, how was it going? It went 1, 4, 7, 10, 13, 16. Now let's look at what the n values were for the indices. We said we were starting at 1. And again, we didn't really have to. You can kind of start at 1 or 0. Sometimes it's just more useful to do one than the other. So if I let n be 1, then this was the second term. This was the third term. This was the fourth term, fifth term, sixth term. And it just kept going. So I'll put dot, dot, dot down like that. What I need is a pattern that will relate the index number to that, to that sequence value. I need a function that will consistently work for all n values. Well, let's see here. We're going up by 3s, right? It seems pretty linear, right? So therefore, a sub n would be 3 times n, right? Because 3 times 3 is 9. 2 times 3 is 6. They're not quite right because I have to subtract 2. Right? That would work. So 3 times 1 minus 2 would be 1. 3 times 2 is 6. 6 minus 2 is 4. 3 times 3 is 9. 9 minus 2 is 7. 3 times 4 is 12. 12 minus 2 is 10, and so on. And you put curly braces around it. And that's your explicit formula. Now note, those formulas are very different from each other, and that's going to be interesting for you because implicit and explicit formulas for the same sequence do not look anything like each other. So make a big note. The implicit and explicit formulas or formulae, depending how fancy you want to be, are very different. But they both work. Now that said, we will want to work with one more than the other depending on what we're doing. So there are reasons why we use one versus the other, but they both work, right? They both are valid. Being real with you, we're going to work with the explicit one way more, right? The explicit one's where our money's at, but we will work with the implicit one some. It's just not as common for us to work with as the explicit one. We're going to work with that one a ton. All right, now I want to show you how to use, speaking of using the explicit formula, we can use Desmos to graph an explicit formula. So let me show you how to make that work. In Desmos, I'm going to add a table. Oops, I'm a little off screen here. I just want to make sure you can see. So I'm going to add a table. And there's a couple ways we can do this. Let me add an expression here. So if we look at our expression, if I say, hey, it's really f of x is equal to x divided by 1 minus 2x, like that. Right? I can say it that way. And down in here, I can say, hey, okay, n1, 1, 2, 3, 4, 5, 6, 7, etc. And then I can make this f of n1 like that. It'll automatically fill it in because it knows what that function is because I named the function. So I kind of cheated my way around it. But it's graphing the function, but the function doesn't exist. The function's continuous. See the difference? That's continuous. That is discrete. Continuous, discrete. See, there's the difference. So we actually don't want the function itself. The function is a continuous thing, and that's not really what we're working with. We want it for discrete values, 1 through 7, and so on. Now, the other way you can do that, let me turn this off. Well, leave it on, I don't really care. Oh, wait, not there. Wrong thing. Press the plus sign. Let me add a table again. I'm going to call this N2 for the heck of it. 1, 2, 3, whoop, 4, whoop, 4, 5, 6. There we go. I got it to work. And then I can go into here and make that function. I can say N2 divided by 1 minus 2 N2. And there you have it. So that works as well. So you can either define the function and then use the f of n1 feature, or you can type with n2 as your variable and it will work, right? And you can see the points for the graph. I didn't put 7 in, but I can, right? As I add 7, it will automatically generate the values, right? Now, obviously you wouldn't want this as your graph because this is terrible. We have all sorts of things we don't need to see. I don't need to see negative x. I mean, going to 10 is fine, but I can see that all my values are between -1 and 0. So why wouldn't I at least show that much? And then I'm going to copy those dots onto the graph. 1 second. And there we have it. And I just made a little table to remind myself how we did this. Now, technically, the calculator can do it as well, but who wants to worry about a calculator when Desmos will be so beautiful and work so well for us? The one comment to make about Desmos is that Desmos does need it defined explicitly. So we have to have that explicit sequence formula in order to make it work.